Then get started with the meeting. It's 7:02. Thank you so much for coming. If you haven't yet, feel free to grab a slice of pizza. I'm Josh, and I'm the president of ACM. And this is our fourth general body meeting. Please go on to acm@uc.org/c to sign in for attendance. It's super important for us that you fill out the attendance so we kind of know who's come to the meeting, and towards the end of the year when we do elections, we know who's eligible to vote and who's not for the next exec board. All these meetings are recorded, so just kind of giving you a heads up. And the recording, slides, and all of that are usually uploaded to acm@uc.org/archive, and they're also available on our YouTube videos. So far, all past 3 meetings are updated on the YouTube. Our mission is to encourage professionalism among tech enthusiasts in a collaborative fashion by facilitating learning beyond the scope of classrooms to develop innovative and inclusive ideas. So we kind of want to give you things or like knowledge that you generally would not learn directly in class. So that's why you come to these meetings, to learn skills that classes may or may not always teach you. What is it? ACM at UC? Hopefully you guys know what ACM is by this point in the semester, but we're the student chapter for Association of Computing Machinery, and we're kind of the computer science programming cool kid community at UC. You don't have to be a CS or tech majors to be a part of it, but mostly CS, IT, and CE makes up our audience or a general body. Some of the events that we do guest speakers. Like today, we have Dr. Boyang Wang talking about his research. We also do ICPC, which is in March of 2022. We also do Revolution UC. We do a bunch of socials, which I'll talk about towards the end of the meeting, and review sessions. ACM Code of Conduct. It's easy enough. We have a harassment-free experience for everyone. Just be nice to everyone and focus on learning. Revolution UC. Brandon, I finally did update our slides with the new logo. So for those who haven't seen it, this is our new logo for Revolution UC and new colors and jars as well. It is returning in spring of 2022, and it is 24 hours of coding, learning, and fun. So definitely come be a part of Revolution UC when we open up the registration. But if you want to be an organizing member, do reach out to me after this meeting or on Slack so that we can talk more about how to be an organizing member for Revolution UC. If you haven't yet, please join our Slack. You can go at acmcincy.slack.com/signup to join our Slack. That's how we usually do most of our communication. And you can also find all our exec on the Slack. So it's easy for you to communicate back to us. Similar thing, also join our Discord. It is relatively new, a year and a half. And it's more casual conversation, but you do get all the news that you would on Slack on Discord as well. So if you haven't yet, please scan the QR code and join our Discord. Guessing no one is. Hopefully everyone is on Discord already. So without further ado, I want to welcome Dr. Boyang Wang so that he can talk about a little bit about himself and his research. Let me pull up his slides. Is that the slide that you want?
Yeah, I'll do this one first. How about the other one?
Yes. The other one is in, I think this folder.
The second one, yes. There we go. All right, I'll talk about the first one. Let me try a little bit. How do I move to the next page? Ooh. Make it first. Okay, let's get started. Thank you for inviting me. It's a great honor to be here. So today, basically, I would like to talk about the the research projects, the research directions, basically we do in our lab. Then I'll talk about one specific paper we recently published. Okay. First, a brief introduction about myself. So I joined UC in 2017, and before I joined UC, I obtained 2 PhD degrees. First one in cryptography from the university in China, and the second one from University of Arizona in electronic and computer engineering in 2017. Before I joined UC, and before I moved to Cincinnati, I used to live in several different places. Tucson, Arizona for a couple of years. And I did my internship with Bosch in Pittsburgh for 1 summer. And I was a visiting student at University of Toronto for a couple of years. And originally, I'm from a city named Xi'an in China. I lead data security and privacy lab. So currently, we have 4 PhD students, 2 master students, and a couple of undergraduate students working on research with me. And primarily, so in general, I work in cybersecurity. And at this point, I'm focusing on the intersection of cybersecurity and AI. So under this umbrella, we have 3 main research directions. The first one here, this is AI-based cybersecurity. So basically, we try to leverage machine learning, deep learning, different machine learning techniques to address specific cybersecurity problems. Okay, and the second direction here, this is called adversarial machine learning, where we try to evaluate different vulnerabilities of machine learning AI systems itself. And the last one here, this is called privacy-preserving machine learning, or privacy-preserving computation in general. So the basic idea here is we would like to provide privacy-preserving algorithms such that users can actually outsource their data to a cloud server, for example, and the server can actually train the machine learning model without learning sensitive data from each individual user. Okay, so those are the 3 main research directions we have at this point. And also today's presentation is relatively informal, so if you have any questions, please feel free to raise your hand and ask. Okay. So next, what I would like to mention here is I'll talk about a couple of examples for each research direction we have. Then again, as I mentioned, I'll talk about one specific paper we recently published. So for this, if we go back a little bit for this first one, AI-based cybersecurity, one example of this is called encrypted traffic analysis. Right. So for example, if you're at home, you could use VPN or Tor secure communication protocols. And normally by using those protocols, you're hoping that if there is an attacker on the network, it cannot reveal which website you're visiting, right? So that's why it is called secure communication protocol. And excuse me, the reason here is that normally if you use VPN or Tor, the destination of the original IP address for the website you're visiting is actually encrypted. And in addition to that, the package, the network package, the content is also encrypted as well. Okay. However, by leveraging encrypted traffic analysis, it's actually possible for an attacker to figure out which website you are actually visiting by leveraging machine learning algorithms and analyzing the encrypted traffic path. Okay, so we'll talk a little bit more about this later. And another project we have for this AI-based cybersecurity, this is called deep learning side channel attacks. So the basic idea here is assume we have this is target device here. Assume we have a microcontroller and it is running encryption algorithms, for example, AES on this microcontroller. Okay, and then if we assume that a passive attacker could potentially monitor the power consumptions when this microcontroller runs encryption algorithms, then this is the corresponding power traces we assume this attacker can obtain. Then based on a large number of power traces from this microcontroller and also training a deep neural network, it's possible for this adversary to actually figure out what is this encryption key, this secret key inside this microcontroller. Okay, so it's actually a very powerful attack here. And another topic we have for this AI-based cybersecurity is called deep learning-based radio fingerprinting. The setting here is that let's assume that we have multiple different transmitters of the same type. For example, let's say we have 3 iPhones, right? And then we have one receiver here in this wireless network, and for this one receiver, it would like to actually authenticate or identify if it receives some wireless signal, it would like to identify or authenticate which transmitter it is, okay, from those existing transmitters in this network. And what we can do here is on this receiver side, we can actually collect some data from different transmitters, then potentially train a neural network and to identify which transmitter it is. Okay, and the reason here is that why we can actually leverage this to authenticate a different transmitter is because each transmitter, although this is all those transmitters are exactly the same type, but each one actually carries certain hardware imperfection. Okay, so due to different, variances we could have in resistors and all those components we could have on this transmitter. Okay, and where in other words, this deep neural network can potentially learn the hardware imperfection of each transmitter. Okay, any questions at this point? Yes.
So when you refer to hardware imperfections, is it related to hardware erosion or something like that?
Not really. So we're assuming that we don't have any hardware trojans on those devices. We're just assuming everyone is still, how to say, benign. But although they are designed exactly in the same way, but when you actually manufacture it, each one has minor hardware imperfection. So that will cause the potentially shifts of those IQ values for wireless transmission. So yeah, so that's a very good question. So here we assume that we don't have any hardware trojans on those devices. But potentially they could have. But here we assume that they don't have. That's a very good question. Any other questions you may have at this point? Okay, so good. Then for the second direction, as I mentioned, this is in general, this is called adversarial machine learning. This is actually a very hot topic in the past 5 or 6 years in both machine learning community and also security community as well. So the basic idea here is we assume that, for example, we have a lot of images, right? So I think you know that for deep learning, we can potentially train a neural network based on a lot of images, then this neural network can actually tell which animal it is, right? So, and if we have a lot of data, the model is actually well trained. And for this adversarial machine learning, here we assume that an attacker can actually add some very small noise to the original data. And for example, if we have images as inputs for a neural network, that means this attacker can actually add some small noise to this original picture of panda in this example. Okay. Then after that, the one on the right. This is the perturbed version of this image. Then if the adversary passes this perturbed image to a well-trained neural network, then the network can actually predict into a totally different class. Although this is still, to humans, this is still panda. Okay, so that's the basic idea of adversarial machine learning. And for our study in our lab, we focus on data in the form of network traffic, especially encrypted network traffic, binaries, and also attacks as well. Just give you one example. For instance, right? So machine learning is actually a very powerful tool for malware detection, right? And there are many ways to represent the data before we actually pass to a neural network. One way to do it is, for example, if we have a PE file, we're going to pass the binary, the raw data directly to a neural network, right? And if we have sufficient data, then the network can have very good performance and can predict the malware and the benign software. Then what we're doing right now here is we're assuming that attacker now can potentially, for example, this is original malware. If it passes this malware directly to the well-trained model, it will actually predict this is malware, right? So then now this attacker, what this attacker would like to do here is to actually modify the binary in this malware such that this malware still has exactly the same functionality, but it will actually force the neural network to actually predict it as a benign, right? Because there are bytes in this binary that this adversary can change, and by doing that, this adversary can actually add perturbations to this neural network. So this is not exactly the same as the image because there are actually additional challenges because we cannot add perturbations randomly, right? So because we want to maintain the functionality of this binary. Okay. Just want to give you one example, and for the privacy preserving machine learning here, as I mentioned, so the basic idea here is assume we have many individual users, and those users, they have data, and maybe they don't have the expertise in terms of machine learning. They don't know how to write a Python code, the TensorFlow, to actually train a machine learning model itself, right? And maybe it does not have a GPU, for example. Then those users, they would like to, a typical way to do that is to actually outsource data to a server. And for example, Amazon, they provide services for users, and the server can actually train a very good model and return the model back to this user, for example, a startup company, right? Then the question here is, what if the data is very sensitive, right? So for example, a startup company may have financial data and health data, and all those things are very sensitive due to different regulations and policies as well. And in that case, what do we do? And one way to potentially to address this is to encrypt the data before uploading the data to the server. Then we ask the server to actually train models over encrypted data without decryption. Okay, so that's kind of like the main idea for this topic. Okay, any questions? Now I'll switch to the other presentation, the slides I have. Make it full screen. All right. So this is actually one of the papers I collaborate with my graduate students. So the title here, this is adaptive fingerprinting, website fingerprinting over a few encrypted traffic. So as I mentioned, normally if we use secure network protocols, for example, VPN or Tor, the network traffic is encrypted. And in addition to that, compared to HTTPS, for VPN and Tor, the destination IP is also encrypted, right? So in other words, if we have attacker on this network, this attacker cannot directly learn which website this user is visiting, okay? However, as I mentioned, by analyzing the traffic pattern, it's still possible for an attacker to actually learn which website this user is visiting. For example, let's assume that we do have a traffic pattern of 2 different websites. And for each one, for website A here, we're going to visit this website twice. Okay, so this is actually the pattern for when this user visits this website and the first time, and then this pattern is actually this user visits this same website the second time, right? And similarly, let's assume that we have another website B, and again, we assume this user visits this website twice, and we have this part here. This is a pattern for the first time, and this pattern here, this is actually the corresponding pattern for the second time. So now, if we take a look, yes.
So are each of those 2 portions of each graph, they're like a single request the user would make to a website, like And then the kind of smaller spikes within it are like if that one request is making several requests.
So you're talking about, for example, this part here, right? So this is more like, for example, we have user Alice. Alice visits, for example, Google using VPN. Then Alice will send some request, and Google will send some corresponding data back, right? And this part here, this is corresponding overall the potential pattern this user will introduce in terms of the traffic path. And this part here, this is like we'll assume that this user will send another request, and it will cause will trigger another corresponding pattern here. Okay. And similarly here, this part here, we're assuming that this user is going to visit another website, and it will cause some corresponding traffic. And here, this is actually the amount of data according to the corresponding timeline here. Okay. And this is the second time for this user for website B. Okay. Any other questions? Yes.
So when you say the traffic is encrypted,
yes.
Would it also be encrypted in, for example, the packet capture file?
What's that?
PCAP file?
PCAP file. So you're talking about so how we can actually.
If there's a snipping, for example, if there's a snipping.
Okay. So that's a very good question. We'll talk about a little bit more about that pretty soon when we talk about the model. But I think in general, so that's a very good question. For example, I think many of you probably know that you can use Wireshark to capture network packages in wireless network because it's always broadcasting, right? So it's very easy to capture those traffic. And here, this is actually a figure that we can generate based on Wireshark, right? And here, again, you can always generate the corresponding PCAP file, and you probably learn the corresponding, you still have the header information for each packet, right? But the content is actually encrypted, right? So does that make sense? Okay. And again, as I mentioned, if you are using VPN or Tor, the original destination, for example, if you are visiting Google using VPN or Tor, if you use a Wireshark to capture that corresponding traffic, the traffic header does not have the corresponding IP address for Google. It only has the VPN, the IP address for the VPN server, right? And your own IP address. Okay. So yeah, again, that's a very good question. So now, based on this very simple example, as you can see here, right? So what do we learn from here? So that means if we visit the same website, if we repeat it, likely we'll have very similar pattern here, right? And the same for website B. And if we compare A and B, between A and B here, as we can see here, each website potentially can offer a very unique traffic pattern. Okay. So now let's talk about the attack model. So here we're assuming that the user uses Tor network or VPN. It's the same concept here, basically. And we assume that we have attacker here on this public network who could potentially eavesdrop the network traffic between this user and the Tor network. Okay. And again, you can assume that we have many users in this classroom, and potentially we have another attacker close to our Wi-Fi network traffic who can actually use Wireshark to capture all those packages from your laptop and from your smartphone. Okay. And so here we assume, since this is a secure network protocol, we assume that this all those the content of those packages are actually encrypted, right? But on the other hand, this attacker can still learn the size of each packet, the direction of each packet, whether this is from your device to the server or whether this is a packet from the server to your device, and also the time of each packet as well, right? Because those information are actually unprotected. And the reason is we need to keep those information in order to actually send those packets to the corresponding correct destination on the network, right? So again, here the attack goal here in this particular problem is to actually reveal which websites a user visits, okay? And normally for this website fingerprinting problem, we can formulate as a machine learning problem. And there are two typical ways to evaluate this. The first one, this is called closed word setting, which will assume that, all right, so this user is going to visit a set of websites, for example, 100 websites. And the attacker knows every single potential website this user is going to visit. Okay, and if this user visits one website, then this is definitely one of them in this set. So that's why it's called closed word setting. And obviously, this can be formulated as a multi-class classification problem where each label is basically a corresponding website, right? And normally, the basic setting here is we assume attacker can actually collect some training data by using its own device and then train a machine learning model. Then after that, if this adversary can capture one traffic trace from this target user, it will try to predict which website it is. Okay, so it's called closed word setting. Any questions? Yes.
I assume that those patterns arise because the host is sending back information in the same order. Like if you the small spike might be some text and then an image all on the same web page.
Yeah, so close. So basically, excuse me. So if we assume that we have the same content on this website, so when the server returns, once a server receives a request from your device, for example, then it will send the corresponding data back to your device. And if it is the same content, so likely it will will trigger the same pattern. So that's the reason, right? So if, for example, we have image 1, 2, 3 on the website, and every single time the website will return image 1 first, return image 2 next, and image 3 the last one. And every single time it will repeat the same thing, right? If we assume the content remains the same. Okay. However, so yes.
Yeah, but also if the website doesn't have the same, for example, a video hosting site where the video, if it's transmitting video to the user, how would the machine learning algorithm be able to figure out that leaving that website? So
that's a very good question. So the question here is you're asking what if the content changes, right? So that's a very good question. We'll cover that a little bit later. We'll also talk about the potential limitation in general for this one. So that's a very good question. So a quick answer here is no. In that case, machine learning model cannot, at least cannot provide a very good performance in that case, because if the content changes, the pattern will change. And for the machine learning model, it's going to be unseen data for the same label. So in that case, it will not provide a very good performance at least. So that's a very good question. Yes?
Yeah, would it be, so I'm thinking with other dynamic content, like if you're loading Facebook.
Yes.
Maybe, like, would it still be able to recognize that if it's always loading like the structure of the page and the header or whatever, and then loading the content later? It could like recognize part of the pattern and just ignore the rest.
So interesting question. I would say depends. So depends on how good your neural network is, and also depends how many data you have. Or in other words, whether your training data can be a very good representation of the potential distribution of the corresponding traffic pattern. So that's a very good question. Another question?
So through analysis of the traffic features, like bytes, you're able to determine what websites are being used by the user. The attacker can then determine what website is.
Yes, okay. So potentially. But talk a little bit more how to represent the data. So yeah, so that's a very good question. Any other questions you may have at this point? So yeah, very good. So here, so this is closed word setting, and obviously, as you can see here, this is a way to evaluate the problem, but obviously it's not very realistic, for example, right? So because we know that we have millions of potential websites on the internet, right? So another more realistic evaluation model here is called open word setting, where we assume that now this attacker still knows a set of websites, for example, 100 very common websites, but now this user may visit a website that is not in this set, okay? So in that case, it can be formulated as a binary classification. Yes, it is in this set, and no, it is not in this set. Okay, so that's called an open world setting. And again, the assumption here is we assume the attacker can actually collect some training data by itself, train a very good model. Then if it has training data from this user, it will actually make the prediction. Okay. So previously, there are several different works working on this website fingerprinting by leveraging traditional machine learning algorithms. So the basic idea here is after we have the corresponding training data, we're going to manually extract the features. So for example, incoming traffic size, outgoing traffic size, number of packages, number of incoming packages, number of outgoing packages, right? Because although for example, the server has exactly the same data, but due to the network condition, the pattern is similar, but not exactly the same every single time, right? So, but still, if we can manually select some features, for example, more than 3,000 features, then we can potentially achieve 85% of accuracy. So that's not bad. Okay. However, some other works, recent papers, they found that by leveraging deep neural networks, we can actually automatically extract features. We don't have to do the manual selection anymore. And in addition to that, if we have very good quality of the data, we can achieve 95% of accuracy in the closed word set. Okay. Just give you a quick description regarding how we can actually describe the data before we pass the data to the deep neural network. Right. So assume we have the corresponding traffic trace, for example, one pickup file that you can capture with Wireshark. Then after that, we can actually represent the data, and so we call it this is binary format, where one means that, excuse me. So one means that this is an outgoing package from your device to the server, and negative one means that it is going to be an incoming package, a packet from the server to your device. Okay, so we call this as a binary format. And the reason that we use this binary format, particularly for Tor network, is because for Tor network, it uses the same package size for every single packet. So it's actually quite secure, robust in this case. But still, even with this, once we have this binary format, so we can still train a very good neural network to learn the potential information. And normally, there is another format here. This is called burst format. So once you have the binary format, you can actually represent data in terms of burst format as well. So the basic idea here is once we have this binary format here, we're going to aggregate the consecutive packages to the same direction together. Then we can have the corresponding format. So for example, if we have 1, 1 here, negative 1, negative 1, that means for the first two packages, we can merge them together. Then we have 2. Then the next 3 packages are going to the same direction. Negative 1 here, so aggregate them together, we have negative 3. Okay, so 2 different formats here. Either one is okay. Yes.
Do you see any performance gain or loss between the binary format and burst format, considering that possibly a binary format might have more time-based encoded into it versus burst format?
So you're asking whether there is a significant difference between this binary format and burst format and potentially other formats that we can represent if we want to do this website fingerprinting, right? So that's a very good question. I think in general, most of the papers, they either use binary format or burst format. It also depends on the protocol. If it is Tor network, so I would say binary format is relatively popular. And if it is VPN, for example, then you can actually, I think burst format is more, potentially has a better chance to have a better performance because in VPN, the packet size is different for each packet. But for Tor, it has the same packet size. So normally people use this. Again, it depends. So, but in general, again, if you have a very large scale data set, then either one is potentially okay, and they can achieve very similar results. Okay. So and also another way to represent a packet traffic trace. So we call it traffic trace here is to actually examine the corresponding time information. So that's another way to represent the data because you have inter-arrival time between each packet. That's actually each two packages. That's actually very different in this entire traffic trace. So that's another way to represent data. But most of the cases, people try to use binary and burst format. But again, time can be another very useful information. Here, as you can see, we only leverage the direction if it is binary, and if this burst format, that means we leverage both direction and size, but we're not including time at this point. Any other questions you have? Okay, so that's a very good question. All right, so now let's talk about the limitations of those existing studies in website fingerprinting. So normally, in order to achieve very good accuracy, so here are the assumptions. We have to assume that the attacker and the user, they have exactly the same network setup. Okay, so or in other words, they have exactly the same operating system, web browser, and also the same version of the web browser as well. And why is that? Because if it is a different operating system and different web browser, for example, attacker has Firefox and the user is using Chrome, then the traffic pattern, even as it is the same website, the traffic pattern will not be very similar. Okay, so that's the assumption we have. So obviously that's a very strong assumption. And in addition to that, we have to assume that attacker is able to collect significant amount of training traces. For example, more than 1,000 traces per website. And normally, with that amount of data, it will take about 10 to 15 days to collect the data for 100 websites in the closed word evaluation. And to make it even worse, normally because all those websites, they update the content. And that means even after 10 or 15 days, you collect one very good data set with a lot of traces. Then that data set is going to be outdated after 2 or 3 weeks due to those changes on those websites. And then with those challenges, then obviously on the other side, for the real world attacker, we know that normally we have to assume that this attacker has different setup and potentially it has fewer traces. And the fundamental research question we would like to answer in this study here in this paper is, can a real-world attacker still achieve high accuracy with different setups and fewer traces, very few traces, right? And the main idea here is to leverage transfer learning, to automatically transfer knowledge that attacker can learn from a previous large-scale data set to a new small-scale data set. So basically try to adapt and to still maintain a good performance here. And our findings here, the main result here is that even with less than 20 traces per website or per classes, when setups are different, so we can still achieve more than 80% of accuracy, which is not bad in this case. Okay. Any questions at this point? Yes.
Is that like you kind of build up like a long-term knowledge of stuff that's from, like in previously you said, websites refresh in like 10 to 15 days. So from before that period, and then you use that to base it on 20 traces from within the last 10 days?
Yeah, so very good. So the basic idea here is assume we have a very large scale data set from last month, for example. And so we're going to train a neural network, right? So we know that if we directly use that for data from this month, probably the performance is not very good. So what we want to do is, but the network still learns something, right? So what we want to do is we're going to adjust this model a little bit with small amount of data from this month, so that it can actually adapt to the data from this month and provide a better performance for the new data from this month. So that's a very good. So that's the basic idea. Okay. So for this transfer learning, here is some basic information. Normally for transfer learning, we assume that we have so this source data. It has large number of traces or samples, right? And for target data, we assume that it has small number of traces. And normally for transfer learning, the assumption here is the source data and the target data, they're different in terms of distribution, but still similar in some way. Okay? Or in other words, let's say if we have images, as the source data could be a data set of images of cars, then the target data could be a data set of images of trucks, right? And because they have some similarity, then we can still leverage some of those features we learned from cars and use that to actually to predict trucks. Okay. However, if the source data is images, is a data set with images of cars, but this target data now this is a data set of encrypted traffic, they are not very similar in that case. We can still apply transfer learning, but I don't think in that case we can have very good performance. Okay, so that's the assumption. And for transfer learning, normally we can have 3 steps: pre-training, training, and test. So pre-training means that we're going to build a neural network with the source data set, the large data set that we have. Then during the training here, we're going to fine-tune the model with some small amount of targeted training data from the small target data set. Then we're, for the last step here, we're going to perform the testing with the neural network on the test data set from the target data set. Okay. So there are actually the basic, normally the basic method for transfer learning here, you probably heard this, is called fine-tuning. The basic idea here is now I have the source data, I'm going to train a neural network, potentially it has n layers, for example. Then during the fine-tuning, what we would like to do is we're going to freeze the first, for example, n-1 layers. Then for the very last layer, we're going to return all the parameters we have on this layer with the data from the target data set. Okay. And this is actually for fine-tuning here, this is actually very efficient in terms of running time. This is very easy to turn the very last layer. However, in many cases, if the data from the target data set is very small, then it does not offer a very good performance in terms of accuracy. Okay, so that's the potential advantage and limitation for fine-tuning. Another typical way to do transfer learning here, this is called triplet networks. And the basic idea here is now for this triplet network, here I have 3 exactly the same sub-networks in parallel. And what we want to do here is during the pre-training here, we're going to learn a very good embedding here by using all those 3 sub-networks. They share exactly the same weights and hyperparameters, right? And then after that, during the training part, we're going to extract this one sub-network out and attach a very simple traditional machine learning cluster, for example, K and N at the very end. Then together, they can actually perform the classification for the target data. Okay. And the advantage of this triplet network here, it can offer very high accuracy in general, but it's very slow in terms of runtime during the pre-training phase because we have to select those triplets. So then you may wonder, what is triplet here? So triplet is actually the corresponding input for this triplet network. So in this triplet here, we have an anchor sample, we have a positive sample, and we have a negative sample here. So this anchor sample and positive sample, they're actually from exactly the same class normally. And this negative sample here, this is actually comes from selected from a different class compared to this anchor sample. And during the pre-training, the goal here for this triplet network is to actually learn a very good embedded space such that the distance between this anchor sample and positive sample, this is very close, or in other words, they are very similar in this embedded space. But for this negative sample and anchor sample here, they're relatively far away in this embedded space. Okay, so that's the basic idea of this triplet network. And so what we use here in this study, we use this, this is another more advanced transfer learning method. This is called adversarial domain adaptation. And the so in this adversarial domain adaptation here, during the pre-training part, we have feature extractor, we have a source classifier, and we have domain discriminator. Okay, so each one is actually a deep neural network. Then we pass both source data and targeted training data to this feature extractor. And the advantage of this adversarial domain adaptation compared to the other two methods here is that it can provide very good, in general, it can provide efficient running time and can potentially offer good performance in terms of the accuracy. Any questions at this point? Okay, so then during the similarly as triplet network, after the pre-training part, we're going to take this feature extractor out, then attach traditional classifier at the very end. Then we're going to use that together to perform the prediction for targeted data. And during this pre-training process for this adversarial domain adaptation here, fundamentally this can be formulated as a min-max game. So basically, we would like to minimize the domain discrepancy and at the same time maximize the source accuracy. Or in other words, during this pre-training here, this is actually a min-max game among this feature extractor, source classifier, and domain discriminator, such that we're going to train a very good embedded space, such that this is very difficult for the discriminator to distinguish the data from the source and the data from the target. But at the same time, we want to maximize the accuracy of this feature extractor and source classifier over the source data. Okay, so that's more like the basic idea for this domain, adversarial domain adaptation. Okay, any questions at this point? Okay, good. All right, so with that, next let's take a look at some evaluations results we have. So here are 4 different data sets. Each one is actually collected with a different setting, and this one here, this is data set, the last one here, AF100, this is collected by our students. Then the first results are from previous papers. And this is more like the high-level information about the neural networks we use for feature extractor, domain discriminator, and the source classifier. Okay, so fundamentally, each one is a convolutional neural network. So if we compare those 3 methods, so in the closed word setting, here n is equal to 1 means that, excuse me, we take 1 sample or 1 trace per class from the target data set, from the new small data set we have. And we can actually try different values of n here. And here's for the source data set, we use AWF100, where we assume we have 25 traces per class during the pre-training. And for the target data set, we use 100 here. And again, n is the number of target training traces we use during the training part. So now if we take a look at the results here, this is actually expected, where for fine tuning, as you can see, it does not have, in general, it does not have offer a very good performance compared to the other 2 methods. But if we increase the value of n here, in general, for fine tuning, the accuracy will increase. For the triplet network here, in general, it can offer very good performance when the data set from the target is extremely small. So that's why it has a better performance when n is 1 here or n is 5. Then for our methods, if we have a little bit more data from the for this n here from the target data set, then as you can see, it can actually offer a better performance compared to the other 2 methods. Okay, so but for triplet network here, there is a significant trade-off in terms of pre-training time, because one limitation, one bottleneck for triplet network here is, as I mentioned, we have to provide those triplets. Normally, we have to select those triplets, and that will normally take a very long time. Okay, and besides, if we go back a little bit, if you take a look at the structure of a triplet network here, you act during the pre-training part, you actually need to train 3 sub-networks in parallel at the same time, so that will lead to a very long pre-training time in general. I'll skip this. And we also compare our those 3 methods in the open world setting. And as you can see here, the black one, this is our method with adversarial domain adaptation. And as you can see here, in general, in the open world evaluation, it can offer a better precision and better recall compared to the other 2 methods. Discussion here, future directions. So normally for transfer learning, one effective way to further improve the performance is to use data augmentation. So basically, based on the data you already have, you would like to generate additional data that can further boost the performance of your model. So for example, if you have one image here, image of cat, you can rotate the image, you can flip it, then you can actually generate another new sample for the same label, for the same class. However, all those existing methods for data augmentation, they do not work directly on encrypted traffic. So for example, we could, for the image of cat, we can actually flip it, then we can have a new sample. But for network traffic, we cannot flip it, right? So because that will not happen in the real world. And in addition to that, we cannot rotate because it's only a one-dimensional data. Right? There's no way for us to rotate it. So that's actually the end of my talk here. In this paper, as I mentioned, this was recently published by my students in this ACM conference, COLA SPY 2021 here. And we do list the link for this paper. We do have the source code and data sets available on GitHub. If you're interested, you can actually take a look at it. And let me know if you have any questions. Okay, so yeah.
Oh, I do have one question.
Yes.
I know you mentioned to me before that you already have sent your students, but in case someone over here wants to get involved in your lab or in your research, what's the best way to do so?
So if you are interested, so definitely send me an email, and then we can talk about those potential opportunities. Yeah. Any other questions you may have? Yes.
So you may have already said this, but I was wondering what classes you teach for undergrads.
So I normally teach data security and privacy in fall this semester, and normally in spring I teach network security. So those are the 2. Well, actually, I also teach discrete math in spring as well. So that's a 2,000 level course. And data security and privacy and network security, those are both 5,000 level and 6 level courses. Yeah. Yeah, so those are the 3 courses I normally teach.
Are there any prerequisites to those courses?
Pretty standard, I would say. I have to check, but pretty standard. I don't have a very hard requirement for those courses actually. Yeah, so typically if you have some background already, if you take those lower level courses already, it's very easy to take those 2 courses. So yeah. Any other questions you may have at this point? Yes.
So I was just wondering, like, what ethical issues, so obviously, as this involves simulated attacks, this is going to involve, some ethical issues and security stuff. So how do you navigate those? Is there like any protocols that you have?
Yeah, so that's actually a very good question. And so I think for our study, when we collect the data, we actually leverage virtual machines, so we don't have to recruit real users at this point. So because that's sufficient, but that's definitely a very critical problem for many cybersecurity studies. So yeah, so that's very good. But at least at this point, for the problems we have in our lab, we don't have to handle that at this point. But that's always a good thing to keep in mind if we do have humans involved in the cybersecurity studies. So that's very important. Yeah, so that's a very good question. Any other questions you may have? Okay. Oh, by the way, one more thing I want to mention is if I go back a little bit. So I mentioned this transfer learning here, the potential discrepancy of training data and test data in this website fingerprinting. And in other AI-based cybersecurity problems, we could have very similar thing as well. So for example, back to this deep learning side channel attacks. So one potential discrepancy it could happen is I'm a attacker if I train, if I collect data power traces from one microcontroller, and if I have a target here, it is exactly the same type, but actually a different microcontroller, a different device. In that case, if I train a model here, it can provide very good performance accuracy for exactly the same microcontroller. But if it is a slightly different microcontroller, again, of the same time, of the same type, and again, due to hardware imperfections of each device, it will cause some discrepancy in terms of power traces. And in that case, the neural network classifier may not provide a very good performance. And in that case, transfer learning, again, can help to mitigate the issue to some degree. Again, it will not completely address the problem, but definitely can mitigate the issue to some degree. Okay, so that's another thing I'd like to mention here. Okay. All right, so that's all I have today, and thank you again for inviting me.
Thank you so much for coming, Dr. Wang. Feel free to grab a slice of the order box. I think we have plenty.
Yeah.
Nice. Again, thanks so much for coming. If you just stick around for a while we close, and hopefully I'll see you around more in the ECS hallway.
Yeah. Well, thank you again for inviting me.
Yeah. And if you have any comments, or is it okay if I like share?
Yeah, for
email
those
ID
two
and
slides,
everything?
yeah, definitely you can share. And if you guys have more questions, feel free to send me an email. So,
Great.
and if you want to do it again next year, I'll be more than happy to come back.
We'll definitely keep that in
We're
mind.
in spring.
No, I think you had good questions, and I feel like people are interested in what you're doing.
All right. I actually need to go.
Okay.
So I'll see you then. Again, thank you.
Yeah, of course. Thanks so much for coming, Dr. Wang.
Good to see you again.
Yeah.
I wanted to say, I've actually got browser fingerprinting.
That's like, oh, I mean,
Using like JavaScript to like fingerprint the browser, emulating a browser, like collecting lots of data and emulating the
All right. Can we all settle down for a few minutes? All right, everyone. Can we settle down for a few minutes so that we can like close the presentation? We still have some stuff left for you guys.
Possibly and so like you could do like keystroke dynamics or possibly also mouse movement like that.
All right. So be sure to join our sibling organization, which is
I'm actually a freshman, so I've just been messing around.
oh, okay.
Yeah.
Okay. So if you wanna do.
all right. Super quick stuff. Be sure to join our sibling organization.
Okay.
If you want to lead a talk or a workshop or have a cool idea, feel free to reach out to me. For our upcoming meetings, for our next meeting, we'll have Dave Agarwal sitting right here, giving a talk on abstraction and programming, or at least that's the TBD topic. I don't know, Dave, if you've like decided on a title yet. Another fun thing is we're doing a pumpkin patch visit on October 17th. So that's going to be a super fun event, social, and we're doing it with ACMW. So it's not just ACM, we're doing it along with ACMW, and it is free of cost, so you don't have to pay anything. It's going to be from 12 to 3 p.m. in the afternoon, I believe, and it's on a Sunday. So I know for a fact you guys don't have classes on Sunday, so be sure to come through. We do have limited seats, so it is going to be on a first come, first serve basis, depending on how many people we can fit in. So sign up as soon as you can. Again, free of cost and super fun way to get to know exec and other people in ACM and ACMW. Just hang out with us in Discord, join a voice channel. If you're working on a project or something, feel free to send a message on that and show off your skills or whatever you've worked on. Talk about classes. I know recently someone was talking about classes on Discord. And if you have favorite memes, feel free to send that as well. ACM execs, huge meme fans. Thank you for coming. If you joined late, make sure you sign in at acm@uc.org/c so that we kind of know who came to the meeting and who did not. And it kind of helps us keep track of our attendance and our selections at the end. Thanks so much for coming. Feel free to grab some more pizza if you want. And I'll be here around for a while if you guys want to talk about something. Recorded.